Hi all, in this video we will be discussing some university questions from Mechanics of Solids. Subject code is CET 201. So I have included altogether 5 questions. 2 is from torsion, 2 is from pure bending, and 1 is from principal stress and principal strain. So first we can have a look on the first problem. So in this question, a solid steel shaft that has to transmit a power of 75 kilowatt which is rotating at 200 rpm. We are asked to calculate the diameter of a shaft, and the shaft is capable to transmit a torque which exceeds 30% of the mean torque. %% of the mean torque, and the power that has to be transmitted by the shaft is 75 kilowatt, and it is rotating at 200 rpm. That is the first part of the question. Second part, it is given in the question that the maximum shear stress in the shaft should not exceed 70 Newton per mm square, and we are also asked to calculate the maximum angle of twist for a shaft of length 4 meter. So these are the given data. So power is given, RPM is given, torque condition is given, and maximum shear stress is given. Okay. So first of all, we can have a look on the given data. So in the question, we are asked to calculate a shaft which is capable to transmit a power of 75 kilowatt. So power that has been transmitted by the shaft is 75 kilowatt. So power is given in kilowatt, so we have to convert the power to our normal units. Usually we will be having the units in Newton, and the distance we are measuring in mm. So you have to calculate the kilowatt to Newton mm. For that, first you have to multiply the kilowatt value to watt. For that, 75 into 10 raised to 3 watts. The watt is Newton meter per second. We want the value in Newton mm per second. So again you have to multiply it with 10 raised to 3. So 10 raised to 3 into 10 raised to 3, you will be having 10 raised to 6 Newton mm per second. Next, RPM is given. The shaft is rotating at an RPM of 200. It is given in the question, 200 RPM. Okay, and the first thing we are asked to calculate the shaft, determine the diameter of the shaft which is capable to transmit a torque of the torque which exceeds 30% of the mean torque. So here you are asked to calculate the T max is equal to, you have to take the condition 1.3 times tau mean. Okay, this condition is like this. We are asked to calculate a shaft which is capable to transmit a power which exceeds 30% of the mean torque. So the torque that has to be transmitted is T max is equal to T mean plus 30% of the mean torque. Okay, so when you take T mean outside, you can have 1 plus 30%. So T mean is equal to 1 plus 30 by 100. So T mean becomes 1 plus 0.3. So you will be having the condition T max is equal to 1.3 T mean. So this is the condition we have to use here. The maximum torque that has to be transmitted is T maximum is equal to 1.3 times T mean. So for calculating this, we have to use the torsional equation. So we have the torsional equation, T by J is equal to Q by R is equal to G theta by L, where T is the torsional moment, J is the polar moment of inertia, Q is the stress developed, R is the distance from the center of the shaft, G is the modulus of rigidity, theta is the angle of twist, and L is the length of the shaft. So this is a normal equation we are considering. So here the first thing we have to consider, or we have to design a shaft which is capable to transmit a maximum torque of 1.3 times the mean torque, and the maximum shear stress condition is given in the question, that is maximum shear value that has to be, shear stress condition is given in the question, it is 70 Newton per mm square. Okay, so initially you have to consider these two values or these two terms for considering or for calculating the diameter of the shaft. So we have the equation T by J is equal to Q by R. So here first we have to calculate the torsional moment or T value. For getting T, we have to use the equation. We have an equation for power. Power is equal to 2 pi n T divided by 60. Okay. Here the power is given as 75 kilowatt. So which is equal to 75 into 10 raised to 6 equal to 2 into pi into RPM. It is given as 200 into T, that has to be calculated, divided by 60. On solving this equation, we will be getting the value for T as 35802.54. Okay, this is the value of torsional moment and it is given in unit Newton mm. So now we have the value for T. Next we have to calculate the value for J. J, it is the polar moment of inertia. For a circular section, the value of J is given by the equation pi d raised to 4 by 32. Okay, where d is the diameter of the shaft. But the thing is, we have to calculate the diameter of the shaft. So ഇവിടെ നിങ്ങൾ d ആയിട്ട് തന്നെ മെയിൻറ്റെയിൻ ചെയ്യുക. Next, the thing is Q. It is given in the question. Q is already given. The condition it is 70 Newton per mm square. That value is given directly. Next, you have to get the R value. Okay, R means if you are considering a shaft, if this is the center of the shaft, the stress value will be increasing and the value will be maximum at the surface of the shaft. So maximum shear stress will be developing at the surface of the shaft, where we can take the small letter r as the radius of the shaft itself. So this r can be given as the diameter of the shaft by 2. Okay, so these are the values that has to be substituted in the equation. Now usually in normal problems we can take the torque as such, but in this question it is given that we have to use this condition, that is T max is equal to 1.3 times T mean. ഈ ഒരു പ്രോബ്ലത്തിൽ നിന്ന് ഈ ഒരു ഇക്വേഷനിൽ നിന്ന് നമുക്ക് കിട്ടുന്നത് എപ്പോഴും ടി മീൻ ആയിരിക്കും. ഈ ഒരു കണ്ടീഷൻ ക്വസ്റ്റ്യനിൽ ഇല്ലെങ്കിൽ നമുക്ക് ഡയറക്റ്റ്ലി ആ ടി എടുത്തിട്ട് സോൾവ് ചെയ്യാം. ഈ ഒരു കണ്ടീഷൻ ഉണ്ടെങ്കിൽ നമ്മൾ മാക്സിമം വാല്യൂ ഓഫ് ടോർക്കിന് വേണം ഷാഫ്റ്റ് ഡിസൈൻ ചെയ്യാൻ. സോ ഹിയർ യു ഹാവ് ടു കൺവേർട്ട് ദിസ്, യു ഹാവ് ടു കാൽക്കുലേറ്റ് ടി മാക്സ് വിച്ച് ഈസ് ഈക്വൽ ടു 1.3 ടൈംസ് our T value. Okay, so when you substitute this value here, you will be getting the maximum torque as 4657,643.31 Newton mm. So this is the value of T that you have to give into the equation T. On substituting the values, T you can give as a T max, which is 465,7643.31 divided by J value, it is pi d raised to 4 by 32 is equal to Q value, that is the maximum shear stress, it is 70 divided by R. R you have to take it as d by 2. Okay, so this 32 will go up. So you can solve this equation like this: 465,7643.31 into 32 divided by pi d raised to 4 is equal to 2 into 70 by d. Okay, so this d and this power 4 will be getting cancelled. We will be getting d cube. Okay, on solving this, we can have an equation for d cube. You will be getting d cube as 465743.31 into 32 divided by pi is here and 140 comes down. Okay, on solving we will be getting d as 70 mm. D as 70 mm. Okay, so the diameter of the shaft, which is capable to transmit a maximum torque of 30, with the torque exceed 30% of the mean torque, the shaft should have a diameter of 70 mm. Next part of the question is also calculate the maximum angle of twist for a shaft or length 4 meter. So for that we can again use the torsional equation, that is T by J is equal to G theta by L. Okay, so here T value already known, J value ഇപ്പോൾ നമുക്കറിയാം because diameter of the shaft നമ്മൾ calculate ചെയ്തിട്ടുണ്ട്. G എന്ന് പറയുന്നത് modulus of rigidity ആണ്, തീറ്റയാണ് angle of twist, L എന്ന് പറയുന്നത് length of the shaft ആണ്. Modulus of rigidity value question തന്നിട്ടുണ്ട്. G is given as 80 gigapascal, okay, which is 80 into 10 raised to 9 pascals. Pascal is Newton per meter square. So when you convert it 80 into 10 raised to 9 Newton, താഴെ meter square ആണ്. So ഒരു 10 raised to 6 വരും mm-ലോട്ട് കൺവേർട്ട് ചെയ്യാൻ വേണ്ടി. So this will be getting cancelled. You will be getting 80 into 10 raised to 3 Newton per mm square. So every value should be in Newton and mm square. So G is known, and here we have to calculate the value for theta. For that we can have the conditions T. We can have the values for T. T is 46.57 into 10 raised to 5 divided by J value pi d raised to 4 by 32 pi into D value നമ്മൾ already calculate ചെയ്തു 70 raised to 4 divided by 32 equal to G into theta. G value it is 80 into 10 raised to 3 into theta divided by L. L is the length of the shaft. It is given in the question as 4 meter. Take it as 4000. Okay. On solving, we will be getting the value for theta. And the theta it is 0.0988 radian. Okay. For converting this value to degrees, multiply it with 180 by pi, you will be getting the values in degrees as 5.65. So, two things to be calculated in the question is, first one it is the diameter of the shaft, that is 70 mm. Next it is the angle of twist, that is 0.098 radian. In degrees it is 5.65. Now we can move on to the second question. The second question is also from the topic shaft. Here we are using a hollow shaft instead of solid shaft. So the question is, a hollow circular shaft of 30 mm outer radius transmit a power of 180 kilowatt while rotating at a frequency of 50 hertz. Outer diameter is given 30 mm. Then allowable stress is 60 megapascal. Megapascal is same as Newton per mm square. And the power it is 180 kilowatt. So in this question, the difference is usually the data are given in the question like instead of 25 hertz. In this question, it is given in the terms of frequency. So when we are having problem like this in terms of frequency, we have the equation for power. Power is equal to 2 pi n t divided by 60. So here usually RPM value will be given, but instead of giving the RPM value, here the frequency is given. So the difference is that we have an equation for omega. Omega is equal to 2 pi n by 60. Okay, and we also have another equation. Omega is equal to 2 pi by t, t for time period, and we know that frequency is 1 by t. So this equation changes. Omega is equal to 2 pi into f. Okay, so if we are substituting 2 pi n by 60 as omega, we can have the equation power is equal to omega into t, and this omega value can be calculated using this equation, omega equal to 2 pi into f, where f is the frequency. It is directly given in the question, that is 25 hertz. Okay, so that is a difference in this problem when compared to the previous one. Instead of giving RPM, it is given in terms of frequency. So once again, P is equal to 2 pi n t by 60. This is the basic equation, where 2 pi n by 60 is omega. When you substitute omega here, we will be having P equal to omega into t. And omega, it is 2 pi by time period, basic equation. Frequency is the reciprocal of time period. F is equal to 1 by t. So omega equal to 2 pi f. So we will be getting the value for omega from this equation. Okay, so we can move on to the problem. In this question, the given data are power is equal to 180 kilowatt. As in the previous case, you have to convert this power into Newton mm per second. For that, 180 into 10 raised to 6 Newton mm per second. Then frequency is given F is equal to, it is given 25 hertz. Then shear stress is given, the maximum shear stress value is given as 60 megapascal. Megapascal is same as Newton per mm square. Okay, then as I told you, first we want to calculate the torque value. For that we can use equation P is equal to 2 pi nt divided by 60. This is the equation for calculating power, where this 2 pi n can be replaced using omega. P is equal to omega times torque. Omega is from the equation 2 pi by t, which is equal to 2 pi f. So 2 into pi into frequency. Frequency value is 25. You will be getting it as 50 pi. Okay, omega value is 50 pi. So we have the power, that is power is equal to 180 into 10 raised to 6 equal to 2 pi n by 60 is omega, that is 50 pi into t. So from here you will be getting the value for t, and the t it is 11.46496.815 Newton mm. Okay, now we have the value for T, and here we are using a hollow shaft, and in this question we want to calculate the thickness of the shaft. So if you are considering a hollow shaft, this is the outer diameter and this will be the inner diameter. Okay, so this value is given in the question as outer diameter, it is radius is given in the question, so outer diameter is 60 mm. It is given as a radius, I think. So diameter of the shaft will be, outer diameter will be 60 mm. And here for getting the thickness, we want to calculate the inner diameter. So outer diameter minus inner diameter will give the thickness of the shaft. Okay, and another difference in this problem, in calculating the value for J, usually we are using polar moment of inertia as pi d raised to 4 by 32. Here, since the section is hollow, we have to deduct the polar moment of inertia of the outer section, polar moment of inertia of the inner section from the outer section. So you will be having the equation as pi d raised to 4 by 32 minus pi d raised to 4 by 32. So when you take this pi by 32 outside, you can have capital D raised to 4 minus small d raised to 4. So this is the equation for calculating the polar moment of inertia. So we can have the equation T by J is equal to Q by R. Here T is the value we got, it is 1.14 into 10 raised to 6 divided by J value, it is pi by 32 into capital D. Capital D is the outer diameter, so you can give 60 raised to 4 minus small d raised to 4 is equal to Q by R, and the maximum stress value is given in the question, it is 60 Newton per mm square. So 60 divided by R. So here you will be having a confusion regarding the value for R, since the maximum stress will be developing at the surface of the shaft. So always keep in mind that R will be the outer diameter, half of outer diameter, that is ഈ ഡിസ്റ്റൻസ് ആയിരിക്കും ഈ ആറിൻ്റെ സ്ഥാനത്ത് നമ്മൾ കൊടുക്കേണ്ടത്. സോ ഇറ്റ് വിൽ ബി ഈക്വൽ ടു ക്യാപിറ്റൽ ഡി ബൈ ടു വിച്ച് ഇസ് ഈക്വൽ ടു എന്താണ് 60/2 ആയിരിക്കും. ഇവിടെ സ്മോൾ ഡി അല്ല സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്യേണ്ടത്, ക്യാപിറ്റൽ ഡി, ബിക്കോസ് മാക്സിമം സ്ട്രെസ് വിൽ ബി ഓൾവേസ് ഡെവലപ്പിംഗ് അറ്റ് ദ സർഫസ്. So on solving this equation, we will be getting the value for inner diameter. So d raised to 4 is equal to 60 raised to 4 minus 580891.197. So here you will be getting d value. D raised to 4 you will be getting a value. For getting d, you have to take either 1/4 or root of 1/4 the root of d. You will be getting it as 51.71 mm. Okay, so now we have the outer diameter and the inner diameter. Inner diameter is 51.71 7 mm. So thickness will be given by outer diameter minus inner diameter. This value is the thickness. Okay, getting the thickness, capital D minus small d. Capital D it is 60 minus small d value will be 51.7. So when you deduct this, you will be getting it as 8.29 mm. So this is a question. We are asked to calculate the thickness of the shaft. For getting the thickness, we have to deduct the inner diameter from the outer diameter. So the main difference in this question when comparing the normal question is, instead of giving RPM, it is given in terms of frequency. Okay, so from frequency you have to calculate P. For that we have the basic equation, P is equal to 2 pi nt by 60. Also omega it is 2 pi n by 60. This is the value for omega. So instead of 2 pi n by 60 we can give this value. So the equation becomes P equal to omega into T. So the thickness, it will be 8.29 mm. So now question number 3. Question number 3 is from PR bending, that is module 4. So in this question we are asked to calculate 4 different things. First thing, we have to calculate the bending stress and we have to sketch the bending stress variation. Second one, we have to calculate the shear stress distribution. Then we have to calculate the bending stress and shear stress at a point 50 mm above the neutral axis. And the last one, whether the structure is safe, because we have given the values allowable shear stress in terms of bending and shear. Okay. So the given data, a simply supported beam of span 5 meter, a uniformly distributed load of 20 kilonewton per meter, 20 kilonewton per meter, and the cross section dimension is 300 mm by 400 mm. 300 mm by 400 mm. So we are having a simply supported beam which is carrying a uniformly distributed load of 20 kilonewton per meter for a span of 5 meter. And the cross section dimension is 300 mm by 450 mm. So first thing, we have to calculate the bending stress distribution. A simply supported beam carrying a UDL of 20 kilonewton per meter for a length of 5 meter. Okay, and the cross section details it 300 by 450 mm. So here the first thing, we have to calculate the bending stress. For calculating the bending stress, we have the bending equation, M by I is equal to F by Y is equal to E by R, where M is the moment, I is the moment of inertia, F is the bending stress, Y is the distance from the neutral axis, E modulus of velocity, and R is the radius of curvature. So here the first thing, we are asked to calculate the bending stress. So we want to calculate the F value. For that we can use equation M by I is equal to F by Y. M by I is equal to F by Y. So for getting F, we can use the equation M into Y divided by I. For that we can calculate M. So we know that for a simply supported beam carrying a UDL, the maximum bending moment value will be WL square by 8. WL square by 8. So the load value is given in 20 kilonewton per meter. It is same as Newton per mm. So 20 into L, it is 5 meter. So take it as 5000 divided by 8. So you will be getting the moment value as 62.5 into 10 raised to 6 Newton mm. Next we want to calculate the I value. I is moment of inertia. So we know that moment of inertia for a rectangular section is simply B d cube divided by 12. So we have B here, it is 300, and D it is 450 cube divided by 12. So your value will be 2278125. Then we want I value, we want Y value. Y is the distance from the neutral axis. So for a beam cross section, usually when a beam sagged like this, usually compressive force or compressive stress will be developing in the top fibers and tensile stress will be developing at the bottom fibers. So neutral axis is a region which is lying in between that of these two regions where the stress value will be 0. That is, stress is neither compressive nor tensile here nature. So Y is the distance from the neutral axis to the extreme fiber, maximum value for Y. So here, since it is symmetrical, Y value will be, you can take the distance from here to top or bottom. So Y will be equal to 450 divided by 2. So your answer will be 225 mm. So here we are having the all values for F. So here F is equal to M it is 62.5 into 10 raised to 6 into Y it is 225 divided by I it is 2278125. So you will be getting F, and the bending stress it is 6.17 Newton per mm square. So this is the bending stress developed in the section, and in the question we are asked to plot the variation of bending stress. So as I told you, if you are considering a beam, this will be the neutral axis. So usually when a beam is subjected to normal kind of loading, top fibers will be subjected to compressive stress and bottom fibers will be subjected to tensile stress. So in the top fibers it will be having compressive stresses, and bottom fiber it will be having tensile stresses, and the variation of shear bending stress will be linear along the depth. So the variation we can plot like this. Here we will be having the compressive stress, here we will be having the tensile stress, and the stress value is given, it is 6.17. If you are plotting compressive stress to this side, plot the tensile to the opposite side. So here also you will be having the stress value as same, 6.17, and it will be varies linearly at the neutral axis, the value will be 0. So this is the variation of bending stress along the depth of the section. So in the first part of the question, we are asked to calculate the bending stress. The bending stress value it is 6.17 Newton per mm square, and the variation will be linear along the depth of the section. Now the second part of the question is, we are asked to calculate the shear stress distribution considering the critical section of a shear. So here in the second part we want to calculate the shear stress value. Shear stress value can be calculated using the equation Q is equal to FA Y bar divided by IB. So this is the equation for calculating the shear stress developed in a section, where Q is a shear stress, F is a shear force acting at this point, A is the area of section, Y bar is the distance from the neutral axis to the area under consideration, I is the moment of inertia of the section, and B is the width of the section. So here, since it is being a simply supported beam carrying a UDL of 20 kN per meter for a length of 5 meters. So in module 3 we have shear force diagram and bending moment diagram. We know that maximum shear force will be, for a simply supported beam, the maximum shear force will be developing at supports. So in this question we are asked to calculate the shear stress at the critical section. Critical section means it is a section where the shear force value will be maximum as per this question. So when you consider a simply supported beam, shear stress will be maximum at the supports. So we want to consider the force F as the support reaction, because here the maximum shear force will be occurring at the support. And for a symmetrical loading, considering it as RA and RB, we will be having RA is equal to RB, and it is given by total load, it is total load by 2, that is 20 into UDL, since it is being UDL, 20 into 5 will give the total load, and it is equally taken by the support, so we will be getting 50 kilonewton. So the maximum shear force developed in this beam will be 50 kilonewton, and it will be happening at the support. So in this question, the critical section will be the support. Either you can take RA or RB, since both are having the same values. Now, so now we have the value for F. Then you have to calculate A, Y bar, I and B. For that, consider the cross section. We want to calculate area of section, and we are calculating about the neutral axis, since for a rectangular section, shear stress value will be always maximum at the neutral axis, and it will be 0 at top and bottom. So we will be considering the value at the neutral axis. So you have to consider the area above the neutral axis. Okay, for that we have the value for F. F, it is 50 kilonewton, 50 into 10 raised to 3 Newton. Then area of the section, this is the area. Okay, area of the section, and area is equal to, so this is the cross section of the beam, it is, this is 300, this is 450. So this will be 225 mm. So area will be 225 into 300. Y bar, it is the distance from the neutral axis towards the CG. So for this area, the CG will be here. So this distance will give the value for Y bar, and will be equal to half of 225 by 2. Okay, we will be getting the value for Y bar, and I is the moment of inertia of the section I. For a rectangular section, moment of inertia it is B d cube divided by 12. Substituting the values, we will be getting it as B will be getting 300 into 450 cube divided by 12, and B is the width of the section or breadth of the section, it is 300. So now we have all values for Q. We have F, area is there, Y bar is there, I is there, and width of the section is there. On substituting the values, we will be getting Q as 0.55 Newton per mm square. So this is the value for Q, and this is the maximum shear stress value, because here we have considered the critical section. Critical section will be happening at the supports, and now we want to plot the variation of shear stress. For that, we have to consider the cross section. This will be the neutral axis, and the variation, as I told you, shear stress value will be 0 at the top and bottom, and it will be maximum at the neutral axis, and the variation will be parabolic. So the graph should go like this, and here it is 0, here also it is 0, and this value will be 0.55 Newton per mm square, and this is the variation of shear stress. Bending stress varies linearly along the depth, shear stress varies in parabolic manner. So these are the two concepts which are clear from this question. In the third part of the question, it is asked to calculate the bending stress and shear stress which is located at a distance of 50 mm above the neutral axis. So here, this is a simply supported beam carrying a UDL of 20 kilonewton per meter. UDL of 20 kilonewton per meter for a length of 5 meter. And you are asked to calculate the bending stress and shear stress at the midpoint. So the question is to calculate the bending stress and shear stress value developing at this point. Okay, and if we are considering the cross section at this section, we will be getting a rectangular section. We will be getting a rectangular section of dimensions 300 mm width and 450 mm. So we are considering the cross section at this point, at the midpoint. Okay, so and here it is asked to calculate the shear stress and bending stress at the midpoint, and the layer which is located at 50 mm above the neutral axis. So actually this is a cross section and this will be our neutral axis, and our question is to calculate the bending stress and shear stress which is located at a layer which is located at a distance of 50 mm above the neutral axis. So at this point we want to calculate the bending stress and shear stress. So from the first two problems we have the the bending stress and the shear stress values. So we know that the bending stress varies linearly. Bending stress varies linearly, and the bending stress diagram is like this. This will be your neutral axis. This will be your neutral axis, and we know that the maximum bending stress is the value it is 6.17. Here also it is 6.17. And in this question, first thing we are asked to calculate the bending stress which is located at a distance 50 mm above the neutral axis. So from this diagram it is very easy to calculate the bending stress. So if you are considering the 50 mm here, so this is your layer under consideration 50 mm. So we want to calculate as it varies linearly, we want to calculate the bending stress developed at this point. Let the value be x. Okay, and this distance it will be 225, half of 450, and this distance will be 50 mm as per the question, giving O here A, B, C, D. Now you will be getting two triangles. One it is OAB, another it is triangle OCD. As we all know, these two triangles are similar. Since these two triangles are similar, the ratio of the sides will be proportional. So length of this side by this side. So you can take x by the property similar triangle, x by 6.17. It will be equal to this height by the total length, that is OA by OC. OA it is 50 and OC it is 225. So for getting x value, we will be having 50 into 6.17 divided by 225, and you will be getting the stress value which is 1.37 Newton per mm square. So this is the bending stress value developed at a layer which is located at the 50 mm above the neutral axis. And the next part of the question is, this is the bending stress. Okay, next we are asked to calculate the shear stress at the same point. As we all know, for a simply supported beam carrying a UDL, its shear force diagram will go like this. If you are considering this as a midpoint, for a simply supported beam, as a shear force diagram varies like this, the shear force value at the midspan is 0. So shear force at the midspan is 0. In this question, we are asked to calculate the shear stress at a layer 50 mm above the neutral axis, which is located at the midspan. So in midspan, since the shear force value is 0, and we have the equation for shear stress, Q is equal to Fa y bar divided by Ib. Here F, shear force value will be 0. So no need to calculate, we will be getting the shear stress at the midspan will be 0. So bending stress at the midspan, which is located in a layer located 50 mm above the neutral axis will be 1.37 and the shear stress corresponding to that point will be 0. And the fourth part of the question, in the fourth part it is asked the fourth part of the question, we want to check whether the structure is safe. For that we have given the allowable stress in bending and shear. So the allowable stress in bending, it is given in the question as 8 megapascal, and the allowable stress in shear stress value is 0.75 megapascal. So this much value is allowable in the structure. That is, bending stress can have a value of 8 megapascal and shear stress can have a value of 0.75 megapascal. As per our calculation, we got the maximum bending stress value developed in the structure, it is only 6.17, which is less than that of 8 megapascal. So allowable it is 8 megapascal, maximum value it is only 6.17, so which is less than the allowable value, so structure is safe in bending. And the maximum value for shear stress, it is maximum shear stress value, it is 0.55 Newton per mm square. In the second part we have calculated for the critical section the maximum shear stress. So the maximum shear stress developing in the structure, actually it is only 0.55, but allowable it is 0.75. So by looking into these two values, 8 megapascal and 0.75 megapascal is the allowable values. For 8 megapascal allowable we are getting only 6.17. For shear stress value 0.75 allowable we are getting only 0.55. So these two values are lesser than the allowable values, so the structure is safe. So the fourth part of the question is asked whether the structure is safe. So the structure is safe when we are considering both the conditions.